Okay, Bill, thanks a lot for this very kind introduction. I'm amazed that somebody like Bill is amazed by what I'm doing, but it's so nice. Thank you, and thanks to Louis for inviting me to this beautiful place. And it's a pleasure for me to talk to you about this microcavity polaritons, which are strange objects that can be considered as atoms or photons, depending on what you want to do. So what is it about? So it's a semiconductor microcavity, so it's a quantum well here, very thin layer of, in that case, indium gallium arsenide placed between mirrors. And in a cavity, the cavity is about one wavelength thick. The wavelength here is 820 nanometers. Okay, so what do the active objects look like in this case? As in any semiconductor, sorry. You have here valence bands, which is full of electrons, and a conduction band, which is free. When one sends a photon here at the right wavelength, one can excite an electron to the conduction band, leaving a hole here in the valence band, and this free electron-hole pair can have very interesting properties, especially in the case we are studying where we send a photon slightly below the band gap here, and then the electron-hole pair saves some energy with the binding energy, and it's a bound electron-hole pair. So it's a negative and a positive charge bound, and from the naive point of view of an atomic physicist, it's a little like a hydrogen atom or positronium, but it should have similar properties. And the good thing here is that because there must be energy and momentum conservation, the K of the photon is this, creates an exciton with the same K. Okay, but this is in the bulk. Now, if in a quantum well, as we have here, which is very narrow, actually in this narrow well here, the levels are quantized, and this conservation is not exactly the same, and the energy now of the exciton is the energy the energy that the exciton has from one of these discrete levels plus the kinetic energy in the plane of the well. Now, in addition, as I told you, these excitons are in a cavity, and in the cavity, they undergo strong coupling. Okay, we have its vacuum Rabi splitting is larger than the decay rate of the cavity and of the exciton. So this is the landscape. And now, in addition, we have to consider what happens. So this is at zero angle. If we shine light perpendicular to the cavity, here is the, and if I look at the energy level as a function of the angle of the K vector of the photon or of the exciton in the plane of the quantum well, the photon has an energy which is parabolic, the usual resonance condition for the photon in a cavity. And here you see what I've drawn is the energy of the exciton. It's flat because we look at rather small angles, and we don't see this h bar 2 K2 over 2 amps. It's just flat. But now, if we are in the strong coupling regime, we have this splitting here. And you see that the upper branch goes up, the lower branch goes down, but it doesn't go down uniformly. Here it gets some of the shape of the photonic band, and we have a coupling between, a strong coupling between these two levels here. So now what are we going to do with that? So the first thing we did, and this started in the in 2000, about 2000, a little before. The idea is that in addition, these coupled states that we have, that I showed you before, which are superpositions of photons and excitons, they have interactions because the excitons, you know, these charged particles, I mean electron and holes, they see each other, and they undergo something like four-wave mixing. That is, when two excitons here, two polaritons here with K, with momentum Kp and minus Kp, for example, hit each other, they can create two other polaritons. So this is just like four-wave mixing, and we have used that to see this generation of other photons in the cavity, because, you know, the polaritons interact, and this gives nonlinearity to the cavity, and it goes like this. Here I have two pump vectors, Kp minus Kp, and here I send two lasers like this, and then here at the output I can have two other polaritons that are created in this dip, which is the dispersion curve, but in 3 dimensions. And of course, it's not necessarily here Kp minus Kp. It can be in other directions. But as you have to conserve the energy and the momentum in this plane here, they have to be opposite and with the same modulus as Kp. So they can have any value here on this circle. So this is what we have tried, and this is what we have demonstrated. If you have, you send two pumps here on the system, on this microcavity, with opposite P's. Here they are hidden, and here if we look at what happens here is because of the type of interactions we have in this case, the emitted polaritons, the created polaritons and the emitted photons have polarization which is orthogonal to the pumps. So if we put a polarizer which is perpendicular to the pump here, we just see the Rayleigh circle, the Rayleigh scattering. And if we look in the right polarization, we see here photons created with two opposites K and in the direction perpendicular to the pump. So it was fun to see these nonlinear effects in rather different situations than what is usually done with atoms, atomic vapors, or atomic ensembles. What we have done is also experiments at normal incidence, and then it was more ambitious because rather than just looking at nonlinear effects, we were looking for quantum stuff. And of course, because when you are in quantum optics, you think, there is nonlinear stuff, four-wave mixing, Kerr effect, I should have squeezing, okay? And as many of us before did some squeezing experiments in atomic vapors, cold atoms, etc., and nonlinear effects producing squeezing. Okay, let's try. So again, this was a rather difficult thing to do because, of course, in semiconductors, you have additional effects, heating, phonons, and so on. But still, we observed bistability here, and we were quite happy to see that just by here. Actually, it's not the laser that is scanned. It's we have a microcavity with the slight angle between the two mirrors, and when you move the laser position on the cavity, then you can sort of scan the tuning. So there is bistability, and close to the bistability threshold here, it was actually in 2004, we observed some squeezing. Actually not very big, a few percent, but we were quite happy because it was far from being obvious. And but then later we did the experiment again with a better system, which is not a single microcavity, but here micropillars. So the micropillars are etched in this kind of cavity. They are very small, a few microns in diameter, and this prevents the phonons from traveling everywhere and heating and bringing additional noise to our system. And again here we saw bistability, and here we scanned the pump power, and we saw this nice noise dependence on the pump power corresponding to the bistability behavior, with here something, as you see, going slightly below shot noise. And it was actually much better than previously. We had a squeezing which was close to 1 dB. So we were quite happy with this new result, showing the capacity of these semiconductors to produce quantum states. But now I'm going to switch to another property of these polaritons to show you the diversity of stuff that we can do with that. And this is quantum fluid properties. So it's quite surprising, and in the beginning we again hesitated to do the experiment. So I'm going back to this strong coupling regime where because of the interaction between photons, here A dagger A, excitons B dagger B, and here the interaction, we have this Rabi splitting between the two levels. Now these photons, as I told you, they have when we just draw the dispersion curve here, the energy as a function of k, the photons have this parabolic shape, and this can be interpreted as an effective mass. I mean, you just write the energy of the photon as a function of k. This second term here can be, I can say it's like a mass, okay, because it gives a curvature to the dispersion curve, and the inverse of the curvature is the mass, okay. And as I told you before, the point is that the lower branch here, which is actually comes from the exciton, but can be, I mean, here when we have excitation at resonance here, both branches here are half photons, half excitons. Here it's half photon, half exciton. It also has an effective mass which comes from the photon. It's not the mass of the exciton. It's the mass of the exciton will appear much further. And so here these polaritons have a mass, but it's the mass of the photon. And in addition, they interact, as I told you before. There is this interaction between the excitons that can be, when you look, so in the experiments that I've showed you before, here the squeezing experiments were done by exciting the system on the lower branch like this here. So and then the Rabi splitting is rather large, and it's larger than the nonlinear effect. So to get the Hamiltonian corresponding to this interaction, we just project on the polariton basis. And so this gives here a coefficient, but this doesn't, actually the coupling caused by interaction, by this nonlinear effect between the two states, the upper polariton and the lower polariton, is negligible. And this is like a photon-photon interaction in the cavity. Okay, so going back to all these properties, so they are superposition of photons and excitons. They have a very small mass, so the mass you find with this simple calculation is about 10 to the 5 the mass of the electron, and this gives a large coherence length at even at 4 or 5K where we are. We put these, of course, we have to work at low temperature, but helium temperature is fine, and this coherence length is rather large. It's 1 to 2 micrometers, while the distance between the polaritons, I mean, if you just calculate just a number, it's a fraction of a micrometer. So in principle, all these numbers correspond to the right numbers to observe condensation, superfluidity, etc. And actually, this has been observed. In 2006, there was this experiment by French and Swiss group demonstrating properties of like Bose Einstein condensation of polaritons, where they excite, they create excitons far from this lower polariton state that I described before, and then they relax to here, and they show that during that time they have an enhancement of the population here. So it was quite controversial for some time, because these polaritons, although they are in a high finesse cavity, etc., they don't live that long, sort of 10 picoseconds, and so can they get to equilibrium at that time? And it was shown later that they do get to some kind of equilibrium, enough at least to justify this paper on Bose Einstein. Actually, not. It's also either Bose Einstein or BKT transition. It was observed in conditions where they didn't make a trap, but the polaritons are actually trapped by some defects around. So, but I won't mention. I won't tell more about that, because what we have been doing is working with resonant or close to resonance excitation of these polaritons. So we excite them with a laser. Of course, it's coherent. We cannot claim that we have created a condensate, but we can show that afterwards it behaves like a condensate. And this was a theoretical paper by Jacopo Carosotto and Cristiano Ciuti. And Jacopo is well known to work a lot with theorists in called atom system, predicting superfluidity of these polaritons in these microcavities. And this could also be connected with the proposal of superfluidity of light that Ray Chow published a few years before that. And so why? So it's just that if you write the equation, the wave equation for these polaritons, here I've written the equation for the lower polariton. It's the what in quantum optics you tend to call nonlinear Schrödinger equation, but it turns out that solid-state people and also cold atom people call it Gross-Pitaevskii equation. So it's just the energy, here the motion, here the potential in which they can be, here the nonlinear interaction, here the decay, and here the excitation. And now, if you look at the solution for the form of, plane wave, the equation can be written like this. And it's very interesting to see that it just looks like the Gross-Pitaevskii equation for superfluid helium for atomic condensates. And then, of course, the next step is to look at Bogoliubov modes. Okay, and the same equation, of course, allows you to write a Bogoliubov operator and find the Bogoliubov modes, which in the case of our polariton dispersion curves allows to predict this behavior where due to these Bogoliubov modes, there is an appearance of a linear here, linear behavior of the dispersion curve, and which then allows to predict this superfluidity. So how does it work? So we start with an idea of exciting here this in this case it's the lower polariton branch. Here it's the laser. So we put it right slightly above the curve because of the light shift, the curve will go slightly up. And this is, and if there is a defect, so we use here to show superfluidity, we look at Landau criterion. So we look at what's going to happen when the polariton fluid that I create with photons going like this on the cavity, then the polaritons will travel through the cavity, like with this velocity here. So in the normal case, when there is not much interaction, if there is a defect, one can see here parabolic waves, and in the far field, the usual Rayleigh scattering ring. Now, in the nonlinear regime, when the interactions between polaritons become large, then there is this linear part appearing, a sound velocity, which is given by the usual value, h bar j psi squared over m square root. And if the group velocity is smaller than this speed of sound, then there are no states available for scattering, and one expects this superfluid behavior where the fluid doesn't see the defect anymore. So this is in the far field, no ring; in the near field, no fringes. So this was the theoretical predictions of this Fitzgerald paper in 2006. Now, the experiment. So this is a scheme of experiments, slightly simplified, but it's not a very complicated experiment because you shine light onto this cavity here, which is in its cryostat, okay, with an angle which will determine the velocity of the fluid. And then you look at the light emitted, transmitted by the microcavity, either in momentum space, far field, or in a real space, image of the cavity ring. And then you can, it's very nice because one can vary the polariton density to go from one state to the other with the pump intensity, the fluid velocity with the laser excitation angle, and then the frequency of the system by changing slightly the laser energy here. And so this is the experiment. With the experiment, you see here that what is observed at low polariton density here is what is predicted here by the theory. So these fringes, just due to the interference of the plane wave of the polariton fluid flowing like this, and of the circular waves. It's 2D, and the circular waves scattered by the defect. And here, when one gets to some threshold, here you see that the fringes disappear, as predicted by the theory, and the polariton fluid doesn't see the defect anymore. And, okay, this is a movie, so I'm not sure I can. Of course, it's a fake movie. It's just several experiments put together. But you see on the right the momentum space where the Rayleigh ring also disappears. Okay, so now, of course, you want to check the full behavior of the system. And what happens when now the velocity is larger than the speed of sound? One expects to be in the supersonic regime where there's still some scattering, but with very specific features, and especially these linear branches here in the fringes. And this is just like a plane at supersonic velocities. And this is the experiment. Again, in the same setup, just increasing the angle of incidence of the laser. And here we see that we have similar fringes as before, but when the intensity is increased, there is this linear Cherenkov wave that appears in the close to the defect. And what is nice here is that the angle of these fringes give us the speed of sound. Just the sign of the angle is CS over VP. Okay, I won't show you the... and this is also similar to Cherenkov waves observed in a BEC some time ago in Cornell's group. And this is very nice because, you know, this gives a speed of sound which is in good agreement with the number that you can deduce from the theoretical value. Because the problem here, of course, is that, okay, the scattering disappears, but it could just be a light shift, okay? The dispersion curve, because of interaction and light shift effect, goes up, and then the laser is not in resonance at that point anymore. But here, the fact that not only the scattering disappears in the subsonic case, but the fact that we observe these Cherenkov waves in the supersonic regime gives the full check of the predictions. And here, so we have a speed of sound which is in good agreement with what can be deduced from these parameters. Okay, now, of course, you would say, but this is just a partial feature because here we have a speed of no intermediate behavior between the two. And what happened is that in this case, in the case that I presented before, the defect was smaller than the healing length. But when the defect is larger than the healing length, here this healing length given by this formula, then additional effects are expected due to turbulence caused by this defect. Actually, what happens is that here, if the velocity is even smaller than the speed of sound, if the defect is large enough, the velocity here can be higher than the speed of sound. So there are several behaviors in the same in the same fluid at different points, and this causes additional effects that we have been able to observe as well with a larger defect. So this is again what was predicted by Carusoto and Tutti. So here we start from the superfluid case, and we decrease the polariton density, so that decreases the speed of sound. So the polariton, which was before below the speed of sound, can be now higher than the speed of sound. But doing that slowly, you see here some intermediate regions where vortices are created here, and here dark solitons appear in the wake of the defect. And so this was the theory, and then we have done the experiment. So the experiment starts again with, in the superfluid case, with a velocity, a group velocity of the fluid which is smaller than the speed of sound, so no effect. Here, when you look at the phase, it's completely coherent. And then the ratio increases, and one has the appearance here of phase dislocations, very visible on this picture here. And when this ratio is increased again, solitons appear. Okay, that can be seen here by phase jumps on this linear thing. And we could study that in detail, compare with theory. And here you see that everything is consistent with the phase jump here observed near this dark soliton and the density of this dark soliton. So that was very nice. Again, a confirmation of the observed effect. So these polaritons really behave like a superfluid system, although there are these strange objects, superpositions of excitons and photons. And we think since they are not so difficult to manipulate, we can also maybe again try to manipulate them like cold atoms. And for example, this can be done again with light. Okay, one can create. In the previous experiments, the defects we had were real defects. So in semiconductors, no problem. You have defects everywhere. Just choose the point where you send the laser, and there's always a dislocation or something that can be as a defect. But you know, if you want to fully control the situations, which you want to do as a physicist, of course, here you can create a defect with a laser. Okay, so here we have a small laser spot, and we have shown that if on this small laser spot, which has a different polarization and in addition also a different, slightly different wavelength than the laser, so it's not here where the fringes we see, it's not interference, it's just the polariton fluid hitting the defect and making fringes. And you can compare the fringes due to an artificial defect, a light effect, and here a real defect. So it's really similar. And the simulation is in good agreement again. And we did that also with a linear defect. So here, defect is here. It's like this or like this, and you see the reflection of the fluid on the defect. And here, we even tried the superfluid regime with the defect, and you see no fringes anymore. So this means that these polaritons can really be also well engineered with light and hopefully trapped also. And before the end, I wanted to give you another property of these polaritons. So what is very interesting in these, as I told you, is like it's photon in, photon out, and inside. So what does the job? And again, it's the photons. Because, you know, as I told you, the excitons, they don't have time to move. So what happens is that in this interaction, okay, you have the wave function, you have the state vectors, which are superposition and so on. But what happens actually is the photons jump from one exciton to the other. Okay, they are absorbed and re-emitted, absorbed, etc. And so it's photons that propagate in this cavity, and they sort of, so with a mass, because this is the effective mass due to the cavity, And then they interact together because the excitons interact together. Okay, so it's interacting massive photons that one can nicely engineer like that, and where one can show properties that are just like hopefully cold atoms. For the moment, I mean, not so clean, but hopefully we will be able to improve that. So this is experiments where we have tried to see how vortices behaved. So first way to fabricate vortices is to, for the moment we don't put by hand orbital angular momentum. We have either beams coming like this or a single beam with a mask in the middle, so that in the end it's like several beams coming from the side. So with a rectangular mask here, it's like 4 beams coming like this, this, and this. And here we have seen also, so this has interference that produce vortices and anti-vortices. So pairs at here, the crossings. And you see here the behavior for low pump power, so the interference fringes, and here the phase diagram, and the vortices can be seen here, the pairs can be seen here, where the phase has this discontinuity. And what happens at higher pump power is that these vortices tend to go further apart from each other, I mean the pairs, and eventually disappear like this. And this is an effect of the going into the superfluid regime where the vortices tend to recombine. We have also done very recently new experiments where this time we inject Laguerre-Gauss beam with SLM, okay, here. So the Laguerre-Gauss beam, in addition, this Laguerre-Gauss beam is like a ring, but in addition we put a Gaussian beam in the middle to prevent the thing from moving. And so what we observe in the at low intensity here is a kind of spiral interference, and here the vortices due to this L equals 8 angular momentum are barely visible. Here they are just circled in green to make them easier to see, but here in the theory one can see better that they are in the dark region, and the phase diagram shows their position. So here it's just nonlinear optics. And now if we increase the intensity, so the population, there's a very clear change in the behavior. Here the interference with the rings with the interferences disappear, and we just see here the vortices. But here it's real vortices. It's really a depth here, low intensity here around these 8 vortices. And the phase diagram is here shown also. And what can be seen when you compare with the previous one is that the ring of vortices is larger. So the conclusion we got with the theoreticians, actually it was theoreticians in Clermont-Ferrand, and they showed that now the interference fringes disappear. What you get are just the vortices created by the light, but they are sort of free. Actually, in theory, there is nothing. They would rotate very fast. here they are sort of pinned by the system, but they still go further apart from each other. And this, we have studied that this is in good agreement with the theoretical behavior. So again, these vortices and their behavior are in good agreement with this model that predicts superfluid and behavior and a sort of system that you can engineer at will in a very nice way. So as a conclusion, I wanted to show you the team in Paris. So this is Alberto Bramati, who is really the head of this group. Alberto Amo did most of the pioneering experiment on this, and he was extremely effective on this. Also, I wanted to thank all the teams we have been working with. So the first is Romuald Doudré from EPFL. It was actually, we started the very early experiment in the 90s that I showed you on nonlinear effects with microcavities that he had made in Lausanne. And they were such an outstanding quality that nobody has been able to make again such cavities since then. We still have them, okay? They are broken, so we use pieces. We hope we are not going, we have a few of them. And Romuald has stopped doing that. So, and actually the fabrication unit in Lausanne is not operating anymore. So, but it's the best microcavities ever fabricated here. And this is the problem when you do semiconductor systems. I mean, you rely a lot on samples. Atoms, you know, you just hope they are pure and then they are all similar to each other. This is not true for semiconductors, and you have to have a good connection with very good fabrication system. And this is, and the next experiments were done with, in collaboration with Jacqueline Bloch, Aristide Lemaitre, and Alberto Amo is now with their team in a lab which is specialized in nanostructures near Paris. And we've been working with quite a lot of theoreticians, Tim Liu and Alexei Kavokin in England, Cristiano Ciuti and his student in another university in Paris, Jacopo, and mention him. And the last experiments with vortices were done with the group of Malpuech in the University of Clermont-Ferrand. And now for other stuff, we have been working also with a nanotechnology lab in Italy. So I'm going to stop there. Thank you for your attention.